Hello, my name is Ethan Chinnis, and this is lab number 5, the world's largest rope swing. The purpose of this lab is to predict the motion of a jumper using the energy principle in a simulation and compare it to the real-life video. And it is also to explain why, in this case, the rope is acting similar to a spring. The results is that the simulation closely predicted the real-life scenario that the jumper would not swing up higher than where he jumped due to the conservation of energy, and also that the rope stretches slightly, acting like a spring. The initial conditions of the system is the jumper and the rope, and the surroundings is none in our simulation, and in real life, there's also air. The mass is 86 kilograms, which is the average adult male mass, which we don't know exactly what the mass is of the person in the video, so we have to estimate. And the initial position is negative 45.72 meters, which I researched and found the length of the rope in the video, and the initial velocity, which is 0 meters per second because he starts from rest. And the spring constant is 600 newtons per meter because that is the average needed in a dynamic rope for a jump this big. And L naught is 45.72, the length of the rope. The principles that we need for this lab is Newton's second law, which is force equal to mass times acceleration, specifically the force of the spring, which is negative K times the stretch of the spring times the L hat, versus the force of gravity, which is Fg is equal to negative mg, as those two counteract each other when the person swings from the rope. And the energy principle we also need, which is delta E is equal to delta K plus delta U, which is also equal to work, where delta K is equal to 1/2 m delta V squared, and delta U is mg delta H. The update formulas we also need for our calculations is that the velocity update formula and the position update formulas, which are here. And we also need our circular motion to understand the what if question, which is mv squared over r. This is the swing that I had to analyze for this lab. You can see the person jump off here and swing. And it's hard to tell from this angle, but the rope does stretch a little bit. The code in this lab is, these are the initial conditions here in the code. And then here is where we get our vector, which is L hat. And then we have this to get our system's energies, which is our K, our potential of gravity, potential of spring, and the total energy. And then we also have the while loop here, which is the main section of the code, which is we have our initial variables, which is K initial, UG initial, US initial, and then energy initial. And then we have our force of gravity, which is mg. And we have our force of the spring, which is the negative K, S, and then L hat, which and it's with S being our stretch. And then we have the net force, which is the spring plus gravity. The ball's velocity update, you can see the velocity update formula here and our position update formula here as from the last slide. And we also have, this is the part where it updates the spring, which is the position minus the spring position is our L, and our L hat is L divided by the magnitude of L. And our stretch is the magnitude of L minus L naught. And then here's where we calculate the energy change, where we calculate our K, which is 1/2 mv squared. And then we have our delta K, which is our new K we just found minus the initial K. And then we do the same thing for potential gravity, which is mgh, and then we do mgh minus our initial. And then we do the same thing for the spring, which is 1/2 kx squared. And then we have our delta spring, which is here. And then we add it all up to get our energy, and then subtract to get our delta E. The results of this code is that we have our spring, which is this ball, which is our person on the end of the spring, which is this ball here, which swings and reaches the exact same point where he started due to the conservation of energy. And we can also see here where the total energy stays constant at 0, with a slight bit of error, which we'll talk about later. And this means that energy was conserved, which means the person doesn't swing higher than where he jumped from. And in the spring simulation works as our model, which means the rope is in fact acting like a spring because it's able to accurately show what happened in the real video. And here's the atoms which show why the rope is a spring, which is all of our atoms are connected by these spring-like bonds between them, which causes the rope to stretch even though it's just a tiny bit with our massive spring constant. The errors in this lab is that one error is that in the simulation, air is not accounted for, which does not account for drag, which means it's slightly different than the real life, which is why the graph has a slightly not straight line at 0. Another error is that the person's mass is estimated, so the total direction, the motion of the person swinging is not exactly like real life because we don't know his exact mass. And what if it were to be even more like a spring? So because the rope is acting like a spring, it has a really high spring constant, which means our radius is staying constant throughout the entire circular motion. However, if we were to reduce our spring constant, which I did here in this simulation, our radius actually changes as he swings. And so you can solve it similarly to how we solve these common tension problems in class. However, we have to account for the changing radius because it is constantly changing throughout the swing. And that is all.